Now that we've looked at how to solve the homogeneous first order ordinary differential equation, we can start getting into some more interesting problems. And the topic of this video is how to begin solving the non-homogeneous case. In particular, I will cover the integrating factor method as described in chapter 2.2 of Greenberg. After viewing this video, I'd like you to know how to recognize and solve a first order linear non-homogeneous ODE, again, using the integrating factor method. So here again, the topic is the non-homogeneous case. And again, the non-homogeneous case has a function on the right-hand side that's independent of y. So this is a non-zero value of q. And it turns out that q serves as a forcing function for any variations in y. And later we'll get into some sort of models of physical systems using an equation like that form, and you'll see where how that forcing function simulates real forcing functions in a mechanical system or an electronic system, actually. Okay, and so the method we're going to use here again is the integrating factor. The integrating factor method. Okay, so there's 3 points that you need to remember when using this method. The first is you're going to multiply the equation by a yet to determined function of x. And this function we'll refer to as sigma of x, and this is our integrating factor. This is the integrating factor that we're going to use to solve the problem. So again, if we multiply the left-hand side by sigma, we get sigma times y prime plus p of x times y, and we also multiply the right-hand side by sigma. That's the first concept that you got to remember. The second concept is that if sigma is such that the left-hand side is a perfect derivative of sigma times y, that is the left-hand side times sigma, is a perfect derivative of the product of sigma times y, then we can, if we know what sigma is, we can solve for y. Because if the left-hand side is equal to the derivative of sigma times y, then we know that the right-hand side is equal to q of x times sigma, and we can solve by simply integrating. So that is, we can solve written in differential form. We have the differential of sigma times y is equal to q of x times sigma dy. Sorry, I wrote that derivative wrong. We got to take the derivative with respect to x. Okay, sorry about that. So the left-hand side is a derivative of sigma times y with respect to x. And if that derivative, if that's true, then we can solve for y because by integration. So again we have the differential of sigma times y on the left-hand side, and then we have q of x times sigma times dx. And therefore sigma times y is equal to the integral of q of x times sigma dx. Okay, so this is how we're going to get our solution. So the first concept was to remember we're going to multiply both sides of the equation by sigma, and if sigma is such that the left-hand side is a perfect derivative of the product of sigma times y, then we can arrive at the solution. But to get the solution, we first have to solve for sigma. So that's the third concept you have to remember. To solve for sigma, we have to use the equation that sigma times the left-hand side of the equation is equal to the derivative of sigma times y with respect to x. Okay, so three concepts, 1, 2, and then finally 3. First we have to solve for sigma before we can solve for y. So now let's talk about how to solve for sigma. So again, the left-hand side was sigma times y prime plus p of x times y. And we said that sigma is such that it is a perfect derivative of the product of sigma and y. And so if that's true, then we get, well, let me write the next step on the next line. So we have sigma times y prime plus sigma p of x times y is equal to, using the product rule, we have sigma y prime plus sigma prime y. And you'll notice that this first term, the first term on the left-hand side cancels with the first term on the right-hand side. And so we're left with and the other aspect is we can cancel out the y's on the second terms. And so we're left with a first order homogeneous ODE of the form sigma prime minus p of x times sigma is equal to 0. So using this integrating factor method, we've reduced a non-homogeneous equation to a homogeneous equation in terms of sigma. And we know how to solve the homogeneous case. I won't go through the steps, but the solution for sigma is just equal to a e to the integral of, in this case, positive p of x dx, because we have the negative sign next to the p. So this is a positive px dx. And here, since any function of sigma will work, any general function of sigma will work, we can make things simple by just setting a equal to 0, or sorry, a equals 1. So we can just make the amount of writing less by just setting a is equal to 1, and sigma will still have the appropriate property that we wanted. We'll still solve this equation. So we've addressed topic 3, and that was to solve for sigma. And now finally we can solve for y, because remember we said that the left-hand side was the derivative of sigma times y, and that is equal to q of x times sigma. And therefore, by integration, we see that sigma times y is equal to the integral of q of x times sigma. And that gives us y is equal to 1 over sigma times the integral of q of x times sigma dx. I need to write my dx in this first integral. So now we add our constant, and this gives us our general solution to our problem. And I recognize that I probably should have described this as step 4, and this is really the last step, and that's to solve for y given sigma. So step 3 was to solve for sigma, and step 4 is actually just to solve the problem. So let's take a look at an example here. And we're going to solve the following differential equation: y prime plus 3y equals x. So again, this is first order. It's a linear differential equation, but it's non-homogeneous because the part that does not depend on y on the right-hand side is not equal to 0. So the first two steps, 1 and 2, we'll do those first. Best to do steps 1 first. And 2 second, and that was to multiply both sides of the equation by a yet to determine function, sigma. So this is the left-hand side times sigma, and the right-hand, and well, that'll equal the right-hand side of sigma, and that's, sorry, the right-hand side of the equation. And we're going to set the left-hand side equal to the derivative of sigma times sigma times y. And then, so we can use this side for step 3, and that's to solve for sigma. And so we have sigma times y prime, that's this part, plus 3 sigma times y, and that's equal to the derivative of sigma times y plus sigma times the derivative of y with respect to x. And again, we see that two terms will cancel. You subtract from both sides and they cancel. And we also see that the y's cancel. And we are left with a first order homogeneous ODE in terms of sigma. So we have sigma minus 3 sigma is equal to 0. So if we do a little algebra here, if we divide both sides by sigma, we get sigma prime divided by sigma minus 3, and then finally sigma prime over sigma is equal to 3. And we can solve this using integration because we see that d sigma dx times 1 over sigma is equal to 3. And then we can multiply both sides by dx, and we get d sigma over sigma is equal to 3 dx. And if we integrate both sides, that gives us the natural log of the absolute value of sigma is equal to the integral of 3 dx, which is equal to 3x. And then normally when we integrate, we have a constant, but in this case, the constant doesn't matter because we just need one sigma that works that has this property. It doesn't matter which sigma, which constant we have up here. We just pick one, and we'll just pick a constant of 0. And so that gives us that the absolute value of sigma is equal to e to the 3x. And again, it doesn't matter whether it's positive or negative. So we'll just pick either one, but we'll pick the positive solution, e to the 3x, because this solution works as well as the negative one, or it works as well as any equation of this form with a constant here. So we'll use this as sigma. So that's step 3. So again, we have sigma is equal to e to the 3x, and we have the derivative of sigma times y with respect to x is equal to the right-hand side, which is q times sigma, and q again was x. That's q of x. And then multiplying both sides by dx. This Leibniz notation for in which we can separate these differentials is very convenient, because we can think of multiplying both sides by this differential x. And so therefore we can integrate, and we get sigma y is, well, let's see, let's substitute sigma in here. So we get sigma, which again was e to the 3x, times y is equal to the integral of x e to the x, 3x, times dx. So now let's solve this integral. And we'll use the method of integration by parts, in which u is equal to x, dv is equal to e to the 3x dx, and therefore du is equal to x, and v is equal to the integral of this, so that's 1/3 e to the 3x. And so again, the integration by parts means that the integral of u dv is equal to u times v minus the integral of v du. So again, we've set u equal to x, and we have this being e to the 3x dx equals dv. And so we get u times v, which is x over 3 e to the 3x, minus the integral of v, du. Sorry, du is not x, du is dx. U is equal to x, so du is dx. And so now we have an integral that we can solve. And we have to remember our integration constant when we evaluate this integral. The constant comes out of this second integral. And so carrying this solution back to our task of solving for y, we have e to the 3x times y is equal to x over 3 e to the 3x minus 1/9 e to the 3x plus c, and that's equal to e to the minus 3x times all of this, And then, but when we evaluate this expression, we get, so this is y. We've multiplied both sides by e to the minus 3x. So the left-hand side gives us y, and that gives us x over 3 minus 1/9 plus c e to the minus 3x. And this is our general solution. Now, that's our general solution, but if we were given an initial condition, if we're given an initial condition, that is y at point A is equal to B, then again we just substitute A in for x, and B in for y, in the general solution, and solve for C. Right? So this is the general solution. If we want the special case in which y is equal to b when x is equal to a, then we just substitute a in for x and b in for y, and then we can solve for c, which gives us our particular solution for that initial condition. Okay, so this covers the solution to the non-homogeneous case using the integrating factor method.